Well, I'd like to start by thanking all the partners who have been involved in the project that you're going to learn a little bit about today. And so that's included the Town of Annapolis Royal, who's serving as the partner on a larger project, which I'll speak about in a moment, and students in the Energy Sustainability Engineering Technology Program, or ESET, at NSCC. So for anyone who's unfamiliar with Clean Annapolis River Project, we're an environmental non-government organization with a mission to enhance the ecological health of the Annapolis River watershed through science, leadership, and community engagement. And we've got a pretty well-defined agenda for today, and I want to get right into the meat of things. So we're going to be making our way through 3 student presentations. We're going to start with the energy audit and recommendations for the Annapolis Royal Volunteer Fire Department, and then move on to Public Works, and then the Town Hall building. And the students have all pre-recorded their videos, so I'll cue them up and play them. In between each of those segments, we'll have a question and discussion opportunity. And at the very end, we can also come back and have some more open discussion as well. And just really quickly to give you an idea of how this work precipitated, I'm going to minimize this gray box on top of Morgan's face. So CARP was fortunate in receiving funding through the Low Carbon Communities Program to support a project in partnership with the towns of Annapolis Royal and Middleton that focuses on energy sustainability planning in both of those towns. Each town has a lot of similar challenges and deals with things like, staff that are just overwhelmed with so much work to do and not necessarily a lot of the kind of technical background required to really dive into energy planning. And we have this great resource so close to us through the ESET program. And so what we've done with this project is been able to partner with students. These are 3 groups of students who are in their first year of a 2-year program. And they've been able to focus on 3 buildings in the town, but our 2 project leaders, Jakeman and Morgan, are going to be doing additional work on assessing other buildings, infrastructure, policies, and practices in order to provide strategies and recommendations so that each of the towns can work to improve their energy sustainability and help to mitigate greenhouse gas emissions. Second phase of this program that'll really get started in the new year will be training and capacity building within each of those towns to make sure that in future years we can actually implement those recommendations. And then another key piece with this is always identifying funding opportunities to make things happen. And so that's another aspect of the project as well. I did also want to acknowledge that the Clean Foundation, through the Clean Leadership Internship Program, has supported this work by providing funding subsidy that's helped us to keep Morgan employed as part of the team. So that's my really brief info, and I'm going to switch over to our first video now. So just excuse me for the momentary gap. Here we go. And actually, I just want to make sure I have this optimized for motion and video. And I'm going to jump right into the video.
Hello, and thank you for being here for the presentation of the energy saving recommendations for the Annapolis Royal Volunteer Fire Department. This presentation was put together by myself, Jack Murray, alongside Corey Pinney, Mel Melanson, and Lucas Yates.
During the audit process in early September, Jakeman Mercer and Morgan Mason contacted the Energy Sustainability Engineering and Technology Program through Chris Humphreys to complete an audit on the Annapolis Royal Volunteer Fire Department. We completed the audit on September 30th, 2020, and it consisted of the following. We interviewed a volunteer firefighter to collect building usage patterns, utility bill information, and ask about the previous upgrades that may have been done. We also collected data on the heating systems and domestic hot water. We determined the insulation material, calculated for the areas of the walls, doors, and windows. As well, we looked at the roof for solar feasibility. There was a light count, and quantities of other small electrical appliances were accounted for as well.
During the interview, we were told there was a 30% occupancy rate, as well as a 21-degree set point and an 18-degree setback. A Bradford White domestic hot water system is used with a capacity of 32 gallons and a seasonal efficiency of 80%. The tank is in the mechanical room and supplies hot water for the entire building. The current space heating system for the fire department is an oil boiler that runs on number 2 oil. The model is a slant fin that has a rating of 186,000 BTUs per hour. The boiler is used to heat the truck bay of the building.
The building envelope has some areas of concern, primarily with the large bay doors. These are the areas that have the most heat transfer, so heat is escaping the building, and they're also the leakiest, so air is able to just pass through. We also, checking the building for solar feasibility, noted that the roof slope is 4.5 degrees, and the building faces 30 degrees east of north, meaning that there's one side of the building that will face 30 degrees west of south, and this side has an area of 4,012 square feet that is solar feasible. And when inspecting the lights, we found that they are primarily LED, which is what we would always recommend. So that's perfect.
When modeling, we used RecScreen Expert version 8. It was used to model the baseline data for the building envelope, mechanicals, lights, and PV system potential to propose upgrades, which we'll speak to now in the recommendations section.
So we have 3 main recommendations that we are going to propose. One of them is within the building envelope, one of them is the PV system, and one of them is upgrades to the mechanical systems. So starting off with the building envelope here, we have upgrades to the bay doors. So we recommend that R8 fiberglass insulation is added to the inside of the bay doors. These can have a vinyl facing on them, so they will be durable and washable, so they will be able to survive within the truck bays. And then we also recommend that rubber sealant is added to the outside of the bay doors to make sure that no air is able to pass through. So we'll need 720 feet of insulation to complete this project on all 5 bay doors there, and that will come to a total of $1,000. Then we will need 180 feet of bottom seal for the garage doors, 60 feet of bottom seal for the garage doors, and 180 feet of side and top seal for the garage doors. This will come to approximately $370. All of this together will give a 11.9 space heating increase in efficiency, which means that $559 will be saved annually, and that means that your money will be made back within 2.5 years. This project is a DIY project, so the firefighters will be able to undergo this themselves, and it will save 5 tons of CO2 per year, which is the equivalent of planting 1.1 acres of forest.
To help offset the costs of electricity, a 20 kilowatt photovoltaic system is proposed to be a viable upgrade. It's modeled using Red Screen Expert and is based on a feasibility approach. The parts and equipment modeled for use for future estimates will be at the discretion of the service provider which conducts them. This includes a structural engineering assessment to ensure maximum roof weight is not exceeded. The PV system upgrade shows that when the total electricity consumption of 167,754 kilowatt hours is offset with the entirety of the building efficiency measures, including that of the solar generation, there's a savings of 51,797 kilowatt hours. This equals a 30.9% reduction in the total energy costs. Excuse me. The total costs of $32,760 are calculated based on information from the Redscape Expert database. Over a 25-year life period and 15-year debt term, the annual savings in revenue are $7,257. The incremental operational and maintenance costs are $330, and we see a net yearly cash flow beginning in year one of $167. What this all means is a simple payback period of 12.2 years. The greenhouse gases reduced by 23% from baseline to the PV upgrade system, which is an equal amount of 14.2 tons of CO2 or 33 barrels of crude oil not consumed.
Upgrades to the boiler could prove more energy and cost efficient. The oil boiler could be replaced with an air-to-air heat pump system. Air-to-air heat pump systems can be tremendously efficient. They can deliver up to 3 times more heat energy than the electricity that it uses. A heat pump upgrade that is around 135,000 BTUs per hour would be sufficient for this building. These upgrades would cost approximately $36,000 at the price of $6,000 each for 6 units. This upgrade will yield a seasonal efficiency of 290% as opposed to an 80% efficiency with the current boiler. Installation of an air-to-air heat pump will net an annual fuel cost savings of $5,747. This brings the system to have a simple payback of 6.3 years to pay off the initial costs of the $36,000 installation. This upgrade is highly recommended due to the large amount of savings and relatively short payback period. This would save 6.8 tons of carbon, which is an equivalent of 2.4 tons of recycled waste.
And so we absolutely recommend that all of these upgrades are implemented together to have the best benefits. So the total cost of the entire project would be $70,000. This is a cash flow diagram here showing what that would look like with the $70,000 implementation, as well as a $9,000 fuel cost saving each year. So you can see that the simple payback is about 8 years until $70,000 is made back. But there is also options to have loans for the solar panels, so we don't necessarily have to spend all $70,000 right at once. And together, all of the upgrades would save 25 tons of CO2 per year, which would be the equivalent of taking 4.7 cars off the road. This is cutting the Annapolis Royal Fire Department's carbon emissions roughly in half. So that concludes our presentation. Thank you very much for listening, and we'll open the floor for questions.
Okay, so we're great. Pat, go ahead.
Yeah, thanks. The $70,000 cost, I got the cost for the heat pumps, And for the renovations to the bay doors, what was the cost of the solar roof? The panels? Is that where I'm missing the bulk of the money to get to 70,000?
So maybe one of the groups, so Lucas, Mel, Jack, or Corey, if you're able to help field the answer to that question. And I think also connected to costs, one of the things I was hoping to find out is when you estimated costs, is that for materials or was labor also estimated into that?
So Corey was the one speaking on the solar array there. He might be having some connection issues. But yeah, I'm not sure the exact numbers that he had, but I believe it was around $30,000 for the solar array itself, plus the installation fees. And then Lucas was the head of the mechanical systems there. So yeah, he estimated 36,000 for the new heat pump systems. And then that would also have the cost of installations. But the bay doors is a DIY project. It can all be sourced from the Home Depot, and it's all advertised as a DIY project, so that wouldn't have any cost for installation.
Okay, thank you.
Great. And we do know Corey is having some internet connectivity issues, so there will be a report we can circulate. And he answered in the chat that of the initial costs, 32,760 are included in the total cost of the projects. So I'm reading that to mean the PV array would cost about 32,760, but we'll confirm that in a report when we get back.
Good, thank you.
Ken, did I see your hand going up?
Yeah, you did. And this kind of follows on from Pat's question a little bit. I mean, when we're looking the DIY project, fine. I think that's just a no-brainer. But when we're looking at heat pumps and the PV, the solar array, seems like you get a lot more benefit for roughly the same expenditure from the heat pumps in terms of cash savings and environmental impact than you do from the PV array. So so obviously resources are always limited, and you want the most bang for your buck and all these things. But in terms of you making recommendations, I mean, are you saying it's worth doing if there's any benefit? Do you say, if payback period is shorter than 15 years is worth doing? What are the metrics for saying, yeah, do it, or just, for a 30% savings, which is what we saw with the solar there, better to just kind of have better practices about turning off lights and setting thermostats? Yeah. How are you deciding when a project is worth doing?
And I'm going to give the group members a moment to think about their answer and compose themselves while I give an answer from our project perspective, because it may be different than the students where they've been asked to work on something and identify recommendations. It may be more the premise of any savings is beneficial. But what we'd like to do with the results from all three of these reports, as well as the additional assessment work, is to really comb through that with representatives from the town and look at other capital grants or other subsidies we could access to do some serious prioritization of what might be recommended coming out of this project. So for the group, though, for this really specific student project, do one of you want to field an answer to that question?
Well, the benefits of adding the solar as well as the heat pump is that if we move to the heat pump for the heating system, we get rid of oil and we're running on electricity. And so the solar will be able to completely offset the cost of the heat pump system. That's kind of what we base the size of the solar system off of. So then ultimately the heating expenses would be zero. And then also to help the heat pumps not have to work as much, we add the insulation to the bay doors.
Yeah.
Right?
So if I understand correctly, then when you were talking about the benefits of the heat pumps, that was including the inputs from the solar array, or was that on its own?
When we were speaking about the heat pumps, I believe we were speaking about the heat pumps with the solar array. Yes.
Okay, thank you.
Great. And Chris, did you have anything you wanted to add on top of that?
Sure. So just to add a bit to it, Ken, the graphs that they were showing, I believe, were these cost savings compared to the existing oil boiler. So the existing oil boiler has an efficiency rating of about 80%. And then the heat pump system it's called a COP, which is an equivalent efficiency rating. And it's 2.5 COP, which is equivalent to an 250% efficiency rate. So that's where it can use, say, 1 kilowatt of electricity to produce 2.5 kilowatts of heat. So that cost savings is just based on what you're going to save in oil costs, changing to a higher efficiency heat pump system. And when looking at all of the upgrade possibilities, we just chose the ones that had the biggest payback.
Yeah.
And put them in, and then the town can have a look at those numbers and decide which ones they want to make happen.
Yeah, certainly, with the town with limited dollars, as always, if they can kind of look at each possible change in isolation, then you can see certainly where you're getting the most for the limited resources you have to apply towards it.
Right. And I think, Jack, that graph that you're showing is just basing the savings on the heat pump switch with the boiler. Is that not one of the graphs that you have shown there? Just the savings, comparing the boiler to the heat pump? Or maybe I'm misunderstanding that.
Again, Lucas was the head of the mechanical systems section there. So I'd have to double check with him.
Yeah, that is just comparing both the oil and the heat pumps, that graph.
Good. Okay. Yeah, I thought so. And then for the PV, Ken, we were just looking at getting off of our grid in Nova Scotia, which still is fairly high in emissions. So and there are rebates available right now as well.
Great. So I am going to move us into our second presentation, which focuses on the Public Works building. So bear with my transition, and then we'll come back for real-time questions afterwards.
Good day. My name is Jennifer Parrish, and welcome to our presentation. I would like to introduce my team, Marshall Allen and Ashley Clark, and we would like to extend our sincere gratitude for the opportunity to speak with you today and for the opportunity to work with CARP on behalf of the Town of Annapolis Royal. As an ESET second-year class at the NSCC Annapolis Valley campus in Middleton, we were approached by CARP to do energy audits on the three of the town's buildings. This would then become a deliverable for our project management class. As a team, we were asked to do the audit on the Public Works building that is located at 144 Victoria Street in the town. During the audit, the building performed well regarding electricity consumption, but extremely poorly regarding the heating consumption. This led us to propose upgrading to the heating system in both the office space and the garage to heat pumps. Energy savings were approximately 54,541 kilowatt hours, with 33,100 of those kilowatt hours savings coming from just the heating consumption alone. Our analysis resulted in, with just an initial investment of about $21,693, they would save $2,500 annually in savings, with a simple payback of 8.6 years for all the upgrades. The building consists of two connected constructions, an office space connected to an unheated garage on the north side, and a heated garage attached by a short hallway to the east. The office space was newly constructed roughly 6 years ago, while the garage is quite a bit older. The specific age of the garage was not clarified. This assessment was conducted to evaluate the site's energy usage and recommend energy conservation measures. As you can see on this slide, it shows some of the examples of the spots where the insulation needs to be taped up to help seal up the building envelope. The objective of this audit is to generate a model of the typical energy use and the base loads of the Public Works building, make energy-saving recommendations, and to generate a report detailing the analysis and our findings. The audit has been performed using all applicable standards of practice, and the report is completed, in which a copy will be provided to CARP's Sustainable Energy Coordinator, Mr. Jakeman Mercer, along with the RET Screen expert file and any other relevant materials. Now I would like to pass it off to Ashley to go into further detail.
Thank you, Jen. Here are the main methods used throughout this project. To start with, we interviewed members of the staff on site and were lucky to have a very knowledgeable interviewee to walk us through the history of the building and its everyday use. We performed a visual inspection of the building, noting the condition of the building envelope and equipment on site, while taking a lighting inventory, noting the wattage and types of light bulbs used. Measurements were taken of the windows, doors, insulation depth were visible, building footprint, and ceiling heights, using measuring tape and laser measurement devices. A thermal camera was used to assess how heat transferred through different building components, and a few of those images are included in this presentation and the report. All relevant information was taken from nameplates for the main equipment on site so they could be appropriately modeled, while Mr. Mercer collected and scanned copies of oil, water, and electrical bills for us to digitize and enter into software. We used Microsoft Excel to do this, as well as other manual calculations, and utilized the Natural Resources Canada software RET Screen Expert to fully model the Public Works building. The heated portion of the Public Works is separated into two main sections connected by a small hallway. In the newer section, there is an office space, bathroom, and break room for the staff. This section was to be found in great condition, with strongly performing insulation built to code and an extra 2 feet of blown-in insulation in the ceiling. In here are a few incandescent light bulbs, while most other lights on site are LED. The bathroom is served by a Rheem water tank located in the heated garage, and the office space is kept warm with electric baseboards. The garage is heated with an oil furnace, with fans located on the ceiling for air circulation. The photos here show a couple of examples of the condition of the building envelope in the garage, which is built on a concrete slab with metal sheathing for the walls and roof, and a large steel beam running from the south side of the building across the roof to the north side. The bottom images show the temperature difference between the main glass of the window and the space around them where the frame is fixed into the wall. The darker blue shows a noticeable drop in temperature. This is fairly typical and easily repaired. There is further damage to the fiberglass insulation around the garage and large gaps around the edges of the insulation as shown on a previous slide and up ahead. The top images highlight the significant temperature difference between the garage and the steel H-beam, especially at the joints of the beams. There is a lot of thermal bridging in this area, as steel is an excellent conductor of heat, causing the beam to pull heat out of the building in winter and pull it into it in summer, making for uncomfortable conditions year-round and an excess strain on the heating loads of the garage. The energy use on site is dominated by heating loads, and due to the poor condition of the building envelope in the garage, the bulk of the total energy load belongs to the oil furnace, which consumes an average of 4,041 liters of oil each year. For the water and electrical loads, the hot water is a very small consumer as it is used mainly for hand washing. While all other activities on site make a minimal impact, the electric baseboards account for 91% of the electricity used at the Public Works. Now, Marshall Allen will be covering the remainder of this presentation for you.
Thanks for the introduction, Ashley. As you all know, my name is Marshall Allen, and I shall be covering the recommendations, financial analysis, and conclusion. First, the recommendations, and the first several can be done for low initial cost and slight behavioral changes. So converting all non-LED bulbs to LED, the outdoor spotlights around the building used for security purposes being on the most, and during prolonged periods of times being the most concern for changing them over to LED. Then the domestic hot water tank and its exposed distribution pipes should be wrapped in order to avoid standby losses. Then, of course, tightening and sealing up the garage envelope by spray foaming the steel studs, the H-frame steel studs that is in the garage, and taping or patching the existing insulation as best as possible. And then, of course, using the ceiling fans in combination with the heating system in the wintertime to ensure a good heating value. And then lastly, of course, the double head heat pump unit in the garage, and then the 9,000 single head heat pump unit in the office spaces, which you will shortly come to find out just how much more effective it is to heat with. This slide is a capture of the red screen expert generated report, and the top picture is displaying the fuel consumption, fuel cost, and greenhouse gas emissions for the base case, proposed case, and the savings when comparing the two, of course, which is at the bottom of the first picture there. So you can see a total savings of 67.7% in the fuel consumption, a total savings of 49.6% in the fuel cost, and a total savings of 44.6% in the greenhouse gas emissions. However, in the second picture there, it is showing the three main energy consumptions for the base and proposed case. And additionally, the fuel savings as well as the fuel saved percentage down at the very bottom. So overall at the very bottom, you can see the total kilowatt hours saved for the building, base case versus proposed case, is 67.7% in total when considering heating and electricity consumption. And lastly, the financial analysis and conclusions. So once all the building upgrades were modeled, the following analysis and numbers were produced. We found an initial cost of $21,693. That includes all the building upgrades we proposed. An annual savings of $2,500 and a simple payback of just 8.6 years. And then again at the bottom here, we're just restating our heating as well as our energy consumption savings in kilowatt hours annually and percentage of the reduction. So me and my colleagues have also sent a detailed report of our findings, analysis, and assessment of this audit to the CARP resource there. So if there's any other additional questions that we can answer now, feel free to ask. And if there are more technical ones that we can't answer as of right now, please feel free to refer to the documents on tutor.
Okay, so that is the conclusion of the second video. So thank you, Ashley, Jen, and Marshall. And I will turn it back over to any questions that people may have. Ken, I see your hand.
Hey, I'm a question guy.
Perfect.
So currently at Public Works, heating is split between heat pumps and then there's a furnace for an oil-powered furnace, which is for the garage space. The recommendation is to go to heat pumps. It seems obvious, it's clear, but what I don't understand is total electricity usage goes down 12%, even though you're so how are you accounting for the energy produced by the fuel? Is you calculating those BTUs and converting to electricity and saying, okay, we're still going to use electricity? Or you see what I'm saying? There's a gap someplace. If we're only heating with electricity once the furnace is gone, how is electricity usage going down?
So I can take the lead on this one as I did a fair part of the analysis on red screen. So I believe what's done in the red screen analysis, Ken, is that red screen converts the heating consumption from the oil furnace, the number 2 diesel oil I believe is used. It converts that into a kilowatt hours of consumption for heating. So that's why you're seeing such the absurd number. And then the reduction of such the absurd amount is because, well, it's due to the combination of the oversized heating furnace of 124,000 BTUs per hour, which is ridiculous for that size garage, as we've seen the fire department's building had a oil furnace, which was just a little bit higher of an output of that. So with that combination, switching over to the heat pumps, using a much more efficient system, you can see a great
and that
savings.
Makes sense. I just wonder how the energy was accounted for.
Yeah, it just tends to be easier to put everything together in one unit there to get an idea of the overall energy savings.
Great.
Any other questions?
So I'm just in the background queuing up the next video and giving you a minute to think of any other questions for this group. And our final video is going to be focused on town hall. So if you think of any questions about the first two, definitely post them in the chat or save them for the end. And I'm going to once again switch over to share our final video.
Welcome to the Town Hall Audit PowerPoint. My name is Trevor Smith, and on behalf of my teammates, I will be presenting our findings to you. Let's get started. Description. Town Hall is roughly 660 square feet. Its front faces northeast. It was built in 1922. It is an old building, but not the oldest in Annapolis Royal. Currently, it is used as a municipal building with a police station in the basement. Building description. Town Hall is 660 square meters. Its front faces northeast. It was built in 1922. Its use right now is as a municipal building with the police station in the basement. The building main systems consist of a boiler, its water pump, 2 heat pumps, and an HRV. Analysis. Here is a list of the systems we found, what they are, and what we suggest as a replacement. The heating system is a 329,000 BTU boiler. We suggest replacing that with a 120,000 BTU air source heat pump. We found that the ceiling's insulation was rated only at R9. We suggest replacing the insulation with R40 or higher. The patio door at the east side has a U value of 4.4. We suggest replacing that with double pane low E windows with U value of 2.6. The total lighting in the building is 22,018 kilowatts due to old CFL or incandescent lighting. With the new LED lights, that will be reduced to 16,845 kilowatts. Boiler upgrade. The boiler was modeled with three 40,000 BTU-hour heat pumps to match the demand of the building. The air-to-water Arctic 040A is what we recommend. It has 54,000 BTU-hour capacity at 130 degrees Fahrenheit. Fenestration upgrade. The fenestration upgrade proposed for the town hall would be low E, you have a U value of 2.28 and be double pane. All wooden frame windows are to be changed to double pane with low E. Fenestration improvements. Existing windows should be recaulked and inspected for damage. Properly maintained windows can provide up to a 10% in savings on a heating load. As windows need to be replaced, upgrade them with highly efficient windows. Electrical upgrades. Replacing all incandescent lights with their respective LED equivalent would improve energy consumption. Removing the second T8 fluorescent light in every fixture in the comfort room would significantly improve the output from that room. Hallways could be fitted with motion detector lights to limit wasted light energy. Results.
Hi, my name is Jason, and I'll be going over the energy analysis that was modeled using Red Screen software, which is designed to model energy savings for buildings. The graph on the left just represents the data table on the right. You can see the base case usage compared to the proposed case. The fuel usage was converted to kilowatt hours by multiplying the oil consumption in liters by 10.63 kilowatt hours per liter, which worked out to 98,000 kilowatt hours for the heating season. Most of this comes from the high energy intensity of the oil furnace. This was calculated using the historical data supplied. By eliminating the oil boiler and upgrading to a high efficiency heat pump, along with the other envelope upgrades, the overall heating load can be reduced to 22,000 kilowatt hours per season. This represents a 77.5% reduction in energy demand. The large drop in energy is representative of the high efficiencies of the heat pump technology. We did not calculate any major cooling load for the building and omitted it for our analysis. The electricity demand, which was also provided from past energy bills, was calculated at just over 22,000 kilowatt hours. We were able to shave 5,000 kilowatt hours off the yearly total by upgrading all existing lights to high efficiency LED bulbs, which represents a savings of 23% annually. The total savings for both heating and electrical usage is just over 81,000 kilowatt hours, or 67.5%, when comparing the base case to the proposed case. Fuel consumption summary. This is the same as the last slide. The graph on the left represents the data table on the right. The fuel usage was just over 9,200 liters for the base case and 0 for the proposed case, with the only heating source to be from the heat pumps, eliminating fossil fuels completely. The electricity increased from 22,000 kilowatt hours to just over 39,000 kilowatt hours, which increases the total electrical demand for the building by just under 17,000 kilowatt hours on a yearly basis. The totals at the bottom shows the cost for the base case scenario to be approximately $12,000 and just over $6,000 for the proposed case, resulting in around $5,500 in fuel savings yearly.
Thank you, Jason. The total greenhouse gases emissions of the building is about 42 tons of CO2, which is from two sources of energy. One is oil and the other is electricity. In the Nova Scotia utility grid, there is 700 grams of CO2 or equivalent of that for each kilowatt hour of electricity. In the proposed case, by changing oil boiler to heat pump, the greenhouse gases emitted by the oil are removed. Therefore, there are 12.2 tons of CO2 less pollutants. This value can be reduced even more through time by shifting from fossil fuel sources to the renewable one. All in all, the study shows that the upgrades can bring energy consumption in this building from 138 megawatt hour down into 40 megawatt hour, which is equivalent to saving $5,500 in fuel costs every year. Saving from the project can pay off the initial cost of the project, which is estimated to be about $37,000. Within the 6 years, the savings from the building upgrades balance the initial cost of the project and from there bring financial advantage for the building. Thank you for listening to this presentation. We are here to answer your questions.
Okay, welcome back, everyone. So thank you, Bram, Jason, and Trevor. If I may, I'm going to start off with a question as a member of a non-technical background. There were two terms I was hoping you might be able to share the meaning of. One was U-value, and one was, I think the term low E was used, and that actually doesn't mean a whole lot to me.
U value is like a rating. It's your R value with 1 over it, I believe. I think Kristen will correct me if that's wrong. And what was the other one, did you say? Sorry?
Low E appeared on one of the slides related to fenestration.
It's a type of, it is a type of window. I believe it's low emission. No, it's something. I actually forgot what it meant.
Low emissivity. Blocks,
Thank you, Ashley.
blocks or allows the sun to come in depending on the climate zone you're in and what you want.
Thank you. That helps me grasp that. I figured it had something to do with like insulating value, but new terms for me. Ken.
Okie doke.
At least one question for everybody. So in this case, the recommendation is to replace the oil-fired burner with a heat pump boiler. I guess you called it air to water, I think. Which obviously, we've got the rads here, so you can get heating to all the building. Cooling isn't a huge factor here. But my question is that recommendation because we already have the water rads and it's an older building, or is it because that's the most efficient way compared, I guess, the other form of heat pumps are air to air? Is it air to water more efficient than whatever the other ones are called, or is that just taking into sensitivity the heritage nature of the building?
Both, actually. Air to water is more efficient, or water to air, and water to water would be even more efficient. And it was modeled because of the cast iron radiators that you have on site.
Okay, thank you.
Paula, I can see your hand. I can't hear you yet, though. Oh, you're not muted. If you have headphones, perhaps try unplugging them and seeing if it works, and vice versa, because we've had that kind of experience sometimes.
Ones with wires sometimes tend to do better.
Let's see.
I did want to make a point and say I'm very glad that for the town hall there wasn't a suggestion to add in solar panels to that very messy roof.
And Paula, if you want to type your question,
We're not touching that.
Yes, I know for that as well, but also even just from a plain solar standpoint, that roof is not very good.
Okay,
That's why it wasn't included in the model. It's just not prepared for that.
Yeah.
Okay, Pat, do you want to go ahead?
yeah. Can I say that I found this very informative, and I think the CARP and NSCC together did a great job on getting all this information together, and I'm sure that all of council will be interested in seeing the stats, and it comes at a particularly good time before we start considering our budget for 21-22. So thank you all, did a great job.
Thank you. And Paula, sorry, your audio's still not coming through. I know, but type it in the chat box and we'll read it out for you and we can still get an answer. So we're just gonna give Paula a moment to type in her question if anyone else has any. This was mentioned, but I do want to reiterate that we're going to be sharing both student reports as well as a broader report as part of this project. So this isn't the only place that information will be coming.
I had a question for the town hall and public works crew. When you guys showed your financial analysis graphs, I saw that there was like a curve in both of the graphs. Was that just assuming? I know I'll see it in the reports, but was that leaving in the percentage for inflation in those?
I believe it was in the town hall.
It was for the town hall?
We did, in Public Works, we did include inflation rates in our financial analysis.
Okay, so I'm reading this question on behalf of Councillor Hafting. This may be a silly question. We rely on coal for electricity. How is the recommendation to switch to heat pumps more efficient? You guys are trying to sell us heat pumps, so you got to convince us now.
I think I can talk to that. Here in Nova Scotia, 26% of electricity right now are from the renewable source. Considering that in our calculation and in the red screens modeling, the final result was showing that still we got 26,000 less in, at least in the town hall GHGs. And by the time, as long as the province going toward the more renewable sources for the electricity, that value can be also be decreased.
The thing with heat pumps is that no matter how efficient your furnace or your baseboards are, so for instance, electric baseboards are 100% efficient, heat pumps are able to extract heat and energy from the air or the water or the ground, wherever they happen to be hooked up. And so you get an effective efficiency of 200 or 300%, which is why heat pumps are a thing all three of us have suggested, because they are, for what we have access to, even if they are on the grid, just really wonderful for your efficiency and for how much energy you're using.
So to wrap those together, essentially, as long as we keep increasing our renewable energy generators for the province and keep transferring our useful things into electricity instead of burning fuels ourselves for it, we're going to continue to reduce our greenhouse gas emissions as time goes on, because both of those things are going to continue to grow and expand. And heat pumps are more efficient than any form of heating than we have at all so far.
I don't know, Chris, if you still wanted to add anything on top of that.
No, I think they've done a very good job explaining that. And just looking at, we calculate when we do an equivalent ECO2 emission for oil and for electricity, basing the efficiency of a hot, forced hot air system, such as the one at the Public Works or the boiler at the fire department. There is still a savings in ECO2s because the heat pump is so efficient. So they did a very good job explaining that.
Great. So maybe to wrap up, one thing I would encourage, particularly the members of staff and council from the Town of Annapolis Royal to think about is what type of questions and other information do you think are really needed to help make decisions? Because when we resume, it's 1 week before we wrap up for the holidays, but when we get ramped up again in the new year, one of the things we'll be looking for is identifying training and capacity building needs. So while your head's kind of in the energy game, think about what you think is needed here, because we'll be asking that sometime in the near future. So I'd like to thank all of our student presenters. It's really great to have the opportunity to leverage your developing expertise and the program. So thank you so much, and we look forward to being able to read and share those reports that you've produced.
I appreciate everything as well. I know I just kind of reached out to people, and the fact that you guys were so excited to hop on, and also like the simple little things of communication and reaching out for questions is very helpful, and it keeps me going in the right direction as well. So thank you to all the students and Chris as well for being a main communication point, and all of the members of the town for coming in watching this.
Hey, so we've officially stayed on our timeline for today. So whatever you're doing for the rest of the afternoon, have a great one, and you'll hear from us again.